Hello friends, welcome to our crash program, chapter number 5, Work, Energy and Power. What is work? Work equation is actually Fs cos theta, or we can say vector F dot vector S. Work is scalar product or dot product of force and displacement. Okay, where theta is the angle between force and displacement. Theta is the angle between force and displacement. A body is displaced horizontally. A body is displaced horizontally with a force F, which is inclined at an angle theta with the horizontal, Then here, what is the component of force in the direction of displacement, or what is the force which is the cause of the displacement? We can resolve the force into two components, F cos theta and F sin theta. Here F cos theta acts in the direction of displacement. So we can say work is defined as the product of displacement and force in the direction of displacement. That is what called work vector F dot vector S. It is a scalar quantity. Work is a scalar quantity and its SI unit is joule and its CGS unit is 1 joule equal to 10 power 7 erg. If force is perpendicular to displacement, then theta equal to 90 degree, then work is 0. Work done by the force is 0. For example, when a particle is revolving around a circular path, the centripetal force acts towards the center, and its direction of velocity is along the tangent. Throughout the motion. So direction of displacement is also in the direction of velocity. So here we can say force and displacement are perpendicular to each other. So we will say work done by centripetal force is always 0. Like that, we will say when a charged particle enters perpendicular to a magnetic field, the charged particle gets a magnetic force F equal to QVB sin theta, and if it enters perpendicular to the magnetic field, theta is 90 degree, that force is called Lorentz force. Then the magnetic force acts as centripetal force and the charged particle starts circulating. So work done by magnetic Lorentz force on a charged particle is always 0 because it acts as centripetal force. Okay, now listen here. If theta is acute, theta acute means theta less than 90 degree, greater than or equal to 0 degree. Then we will say the work is positive. Positive work. If theta equal to 0 degree, then we will say work is maximum, because cos 0 is 1, work will be F into S, force into displacement. That means the work is completely done by the force. Work is completely done by the force if theta equal to 0 or maximum positive work. And if theta is if theta is obtuse, obtuse means theta less than or equal to 180 degree and greater than 90 degree. Less than or equal to 180 degree and greater than 90 degree, we will say the work is negative work. Why negative work? The work is done against the force. The work is done against the force. That means if we are applying a force, work acts opposite to the, or body displaces opposite to the direction of force. If theta equal to 180 degree, then we will say the work is minimum. The work is minimum if theta equal to 180 degree. Okay. Now we can go into an example. A mass is pulled with a force F. It is inclined at an angle theta with the horizontal. Then the block moves horizontally a displacement S. Moves horizontally a displacement S. S is the horizontal displacement. The angle between force and displacement is theta. F is the applied force. F is the applied force. So we can say work done by the applied force is positive. Work done by the applied force is positive. And what is the work done by the gravity? Here, gravitational force acts vertically downwards. So what is the angle between gravitational force and displacement? 90 degree. So we can say work done by gravitational force Fg is 0. Work done by gravitational force is 0 here. And here we can say there is one more force opposite to the direction of motion, that is frictional force. Frictional force. What is the work done by the frictional force? Work done by frictional force is negative. Why? It acts opposite to the direction of displacement. So here a single process is actually happening. What? A body is given a force for a horizontal displacement S, and the applied force is at an angle theta with the horizontal. Okay, and we can say three types of work in a single process that I explained here. When we are drawing graph between force and displacement, we will get area under the graph. Area under force displacement graph is always equal to work done. Area under force displacement graph is always work done. And for constant graph, for constant force, shape of the graph will be, a straight line parallel to displacement axis. Okay. Now, for uniformly varying force, shape of the graph is a straight line inclined to both the axes. Shape of the graph is a straight line inclined to both the axes. This is the condition for force is increasing uniformly, and I can draw a graph like this also if the force is decreasing uniformly. Okay, so here In both cases, we can say graph is inclined to both the axes. So, if we are finding area under the graph, we will get work done. For uniformly varying force, work done equal to average force into displacement. Average force into displacement, or F1 plus F2 by 2 into displacement x. Okay, here is the question. Graph between force displacement, the graph force displacement is given. Displacement is in meter and force is in Newton. This is the shape of the graph. 1, 2, 3, 4, 5, 10, 20, 30, 40, 50, etc. Okay. Here question is, find the work done from the displacement 2 meter to 4 meter. Here is the graph. Force in Newton and displacement in meter. Force is uniformly increasing. Find work done from 2 meter to 4 meter. This is the question. Here we can apply two methods. We can use the equation or we can use area under the graph. So first I am using that equation. For equation we will use work done equal to average force F1 plus F2 by 2 into displacement x. But it's displaced from 2 meter to 4 meter, right? At 2 meter the force is 20. So F1 is 20 and at 4 meter force is 40. 20 plus 40 by 2 into, what is the displacement 2 to 4? Displacement is 2 meter. So 2 cancelled and we will get 20 plus 40, 60 joule is the answer. Or you can use area under the graph method. Here, which area we have to find? This is the area. You can find area of this portion. This area you will get the correct 60. Okay, this area you can use trapezium equation or you can take this area as a rectangle and a triangle. Then you will get the equation, the same value 62. For non-uniformly varying force, we can't say a perfect shape or regular shape for it. Shape of the graph will be irregular. So to find the area under the irregular area of irregular shapes, we have to use integration. So for non-uniformly varying force, work done is find using integral f dot dx. Integral f dot dx. Integral x1 to x2 from initial position to final position f dot dx, and this is done. This is done when force is given as a function of displacement. We already displaced in the second chapter motion in a straight line that integration and differentiation should be used when there is a function. So here, if force is given as a function of displacement, then that force is non-uniformly varying force. So to find work done, we have to use the equation integration integral x1 to x2 f dot dx. Okay, here is a question. Force is given by the equation. Force is given by the equation 7 minus 2x plus 3x square Newton. This is the force, and the body displaces from 0 to 5 meter. X equal to 0 to 5 meter. Then what will be the work done by the force? We just pause the video and we try to find the solution. Okay, we know that integral x raised to n dx equal to x raised to n plus 1 by n plus 1. X raised to n plus 1 by n plus 1. We have to increase the power with what? N plus 1, and we have to divide with that power n plus 1, x raised to n plus 1 by n plus 1. And we studied that integral dx equal to x. Integral dx equal to x. That you have to apply here. So work done. I'm writing the answer. I think you got the answer. Okay. We have to integrate. Integral from word to word. 0 to 5. 7 minus 2x plus 3x square dx. So we will get 7 dx. 7 is constant, we will take outside, then we will get integral dx. Integral dx is x. 7 into integral dx is x. 7x minus 2 into integral 2x dx, 2 taken outside, so integral x dx. Integral x dx, x raised to n plus 1 by n plus 1. So here x raised to 1, so x raised to 1 plus 1 is x square, and we have to divide with that power by 2, plus 3 into x square, so we have to increase the power, x square, x raised to 2 plus 1, x raised to 3 by 3, and I have to give the lower limit and upper limit 0 to 5 by giving a square bracket. Now you can cancel 2 and 3. Now you will get 7x minus x square plus x cube, lower limit 0, upper limit 5. Now we have to give the values, upper limit and lower limit. First we will give upper limit minus, we will give lower limit. So we will get here work done equal to 7 into, instead of x, 5 minus 0 minus x square, 5 square minus 0 square is 0 plus x cube, 5 cube minus 0 cube inside the bracket. And by solving we will get 7 into 5 is 35 minus 25 plus 5 cube is 125. 125 minus 25 is 100 plus 35 is 135 joule. Next is a comparison between conservative forces and non-conservative forces. Okay, as the name of conservative forces indicates, conservative force will not make any loss in mechanical energy in the form of sound, heat, etc., because they are called that is why they are called conservative force. But non-conservative forces will make loss in mechanical energy in the form of sound, heat, etc. For example, gravitational force is conservative force. Gravitational force is conservative force, and all types of frictional forces are. All types of friction are the examples of non-conservative forces, and we can say nuclear force is also non-conservative force, because nuclear force is the force which binds the nucleons, and in nuclear reactions a tremendous huge amount of heat energies are developed. Examples are nuclear fission and nuclear fusion reactions. Okay, now gravitational force, another example of conservative force is spring force, or we can say elastic force. It is also conservative force. Okay, conservative forces, work done by them does not depend on the path. Work done by the conservative force independent of the path. Work done by conservative forces are independent of the path, but work done by non-conservative forces depends on the path. For example, we can say when a particle, when a mass m is raised to a height h, work done by gravity, Fs cos theta, the force should be mg, and displacement is height, and cos theta is -1, because gravitational force acts downwards and body is raised upwards. Force and displacements are in opposite direction. So work done is mgh into -1 cos 180. So here work done is minus mgh. Work done is minus mgh, and work done against gravity is plus mgh. If the same mass is raised to the same height using this path at an angle theta from the horizontal, in case of gravity both the works are same. Why? With the force of gravity we are taking only the perpendicular displacement. That is why path is not a matter from work to work. Initial positions and final position do matter in case of conservative force. But in case of non-conservative force, paths are also important. So here we can discuss a question, a well-known question, and which is very important question, that a body is displaced from position A to position B through three paths. Path number 1, path number 2, and path number 3. A body is displaced, a mass is displaced from A to B. Okay, if the force is conservative, force W1 equal to W2 equal to W3. Three works are same because conservative force is independent of the path. But in case of non-conservative force, W2 is greater than W3 is greater than W1. W2 second path is longest and first path is the shortest. So W2 is greater than W3 than W1, because non-conservative force depends on the path, not only the initial and final positions but also on the path traveled or displaced by the force, the body. Okay, next portion is energy. Energy is actually capacity of doing work. Its unit and dimensions are same as that of work. And there are some more practical units instead of joule. Okay, joule is a SI unit and erg is the CGS unit. And here are three practical units: EV, electron volt; kilowatt hour and calorie. Okay, see here 1 electron volt is 1.6 into 10 power minus 19 joule, 1 kilowatt hour is 3.6 into 10 power 6 joule, 1 calorie is 4.2 joule, or at the correct value is 4.186 joule. These are the practical units of energy. According to Einstein, E equal to mc square, where E is the energy and m is the mass. That means energy and mass are convertible, or energy can be converted into mass and mass can be converted into energy, and c square is the conversion factor. C square is the conversion factor when energy is converted into mass. Okay, so according to Einstein we can simply say mass is another form of energy. Mass is another form of energy, and energy can be converted into mass and mass can be converted into energy. Mass can be converted into energy. Here c is the speed of light in vacuum. Okay, value of c is 3 into 10 power 8 meter per second. 3 into 10 power 8 meter per second. So if 1 kilogram is changed into energy, if 1 kilogram is changed into energy, we will get 1 kilogram into c square. We will get 9 into 10 power 16 joule, a tremendous amount of energy. So we can say mass is a compressed form of energy. Compressed form of energy. And if we are converting 1 gram into energy, what will be the amount of energy you are getting? 1 gram is 10 power minus 3 kilogram. Into c square, 9 into 10 power 16, we will get 9 into 10 power 13 joule. 9 into 10 power 13 joule. And the smallest unit of mass is atomic mass unit, 1 AMU, or simply 1 U, unified mass, and its value is around 1.67 into 10 power minus 27 kilogram. 1.67 into 10 power minus 27 kilogram. When this mass is converted into energy, what will be the amount of energy that we are getting? 1.61 AMU. We will get this value, 1.67 into 10 power minus 27 into 9 into 10 power 16 joule. 9 into 1.67, we will get around 14.9 something. Okay, 14.9 something into 10 power minus 27, 16, we will get minus 11 joule. And this we can round 15 we can round off into, we can write as 1.5 into 10 power minus 10 joule. 1.5 into 10 power minus 10 joule is the energy liberated when 1 AMU mass is completely converted into energy. And this energy we can convert into electron volt value. So 1.5 into 10 power minus 10 divided by 1.6 into 10 power minus 19 EV. To convert joule into electron volt, we have to divide with 1.6 into 10 power minus 19. Then we will get this value around 0.9315 into 10 power 9 EV, or we will get 931.5 into 10 power 6 EV, or 1 AMU when we are converting into energy, we will get 931.5 mega electron volt energy. So if 1 kilogram is converted into energy, we will get 9 into 10 power 16 joule. 1 gram is converted into energy, we will get 9 into 10 power 13 joule, and if 1 AMU is converted into energy, we will get 1.5 into 10 power minus 10 joule, or it is equivalent to 931.5 mega electron volt. Mechanical energy is classified into two: kinetic energy and potential energy. Kinetic energy is the energy possessed by a moving particle, and it is given by the equation Ke equal to half mv square. We know that momentum P equal to mass into velocity. So when I am multiplying the numerator with m square v square divided by one more mv is momentum. So we can say kinetic energy equal to p square by 2m. Kinetic energy equal to p square by 2m, or kinetic energy equal to half mv square. If two masses are moving with the same velocity, so we can say kinetic energy is directly proportional to mass if velocity equal to constant. If two masses are moving with the same momentum, then kinetic energy proportional to 1 by m if momentum equal to constant. Why? Kinetic energy equal to p square by 2m, mass comes on denominator. That means if two masses are moving with the same velocity, bigger the mass, larger the Ke, and if two masses are moving with the same momentum, bigger the mass, smaller the Ke, kinetic energy. If a body is initially moving with velocity u, and its velocity changes to v because of an external force, then what is change in kinetic energy? Change in kinetic energy means final kinetic energy minus initial kinetic energy. Final kinetic energy is half m into final velocity square minus initial kinetic energy half mu square. So we can take half m outside. We will get v square minus u square. What is v square minus u square? We studied that v square equal to u square plus 2as. V square minus u square is 2as. So we will get half m into 2as. 2 cancel. Ma is force. Force into displacement, that is work done. So we can say change in kinetic energy equal to work done. Change in kinetic energy equal to work done. This is called work energy theorem. This is called work energy theorem. Now listen here carefully. According to Newton's first law of motion, every body continues to be at rest or in uniform motion, in the state of rest or uniform motion, unless compelled by an external unbalanced force. That means if a body is moving with constant velocity, there is no net external unbalanced force. If a body is changing its velocity, there should be an external force. So here we can say, if a body is changing its velocity, then kinetic energy should change. So it is the reason reason is the work done due to the external unbalanced force. So we can say work energy theorem is the consequence of Newton's first law of motion. A running man has half the kinetic energy of that of a boy of half of his mass. The man speeds up by 1 meter per second so as to have the same Ke as that of the boy. Find the original speed of the man? That is the question. By pausing the video, just try to solve. Okay, I think you got the answer. Doing okay. A running man. Kinetic energy of the man equal to half of kinetic energy of the boy. That is the first condition. A running man has half the KE of that of a boy. Okay. So kinetic energy of man, we can say equation half mv square. For man I am giving capital M and capital V equal to half into kinetic energy of boy, half into mass of boy small m, velocity of boy small v, half mv square. Okay. 1/2 is cancelled. Capital M into capital V square equal to half into boy of half of his mass. Mass of boy is half of the mass of the man. So small m is actually capital M by 2. So capital M by 2 into small v square. So capital M is also cancelled. So we got capital V square equal to small v square by 4. So capital V equal to what? Small v by 2. Here we have to find what? Original speed of the man. Capital we have to find. Okay. The man speeds up by 1 meter per second. In second case, man increases his speed by 1 meter per second. Then his kinetic energy becomes equal to kinetic energy of the boy. So we can say kinetic energy of the man, new kinetic energy KEM dash equal to kinetic energy of the boy. There is no change in the kinetic energy of boy. Okay. So half into mass of man into new velocity of man v dash square equal to half into mass of the boy is small m and his velocity is small v square. Okay. Here it is capital V dash. Okay, now half cancelled. Capital M into capital V dash square equal to small m is actually capital M by 2, and what we can do is small v. Here capital V equal to small v by 2. So small v equal to 2 into capital V. Small v equal to 2 into capital V, that we can substitute here 2 into capital V whole square. 2 into capital V whole square. So capital M is cancelled. Capital M is cancelled. What is V dash? V dash is actually V plus 1, because the man increases his speed by 1 meter per second. So V plus 1, old speed plus 1 is actually the new speed of the man. So V plus 1 whole square equal to 4V square by 2, or we will get 2V square. So V plus 1 equal to root 2 capital V. 1 equal to root 2 capital V minus V. 1 equal to V into root 2 minus 1, or capital V equal to 1 by root 2 minus 1 meter per second. Capital V is the actual or original speed, initial speed of the man. Or we can give values here also. 1 by root 2 is 1.414, 1.414 minus 1 is 0.414, 1 by 0.414 meter per second. 1 by 0.5 is actually 2. Here 1 by 0.414, the value will be greater than 2. The value is around 2.42 meter per second. This is the original speed of the man. And here is a question. If momentum of a body increases by 50%, Then what will be the percentage change in kinetic energy? What will be the percentage change in kinetic energy? How to calculate these type questions? We are asked to find percentage change in kinetic energy. So the authorized method to calculate percentage change is delta Ke, change by original into 100%. Change by original means kinetic energy final minus Ke2 minus kinetic energy initial Ke1 by Ke1 into 100. Here we have to give the values. Then we will get the final result. Initially kinetic energy Ke1 we can give P1 square by 2m. Initial momentum is P1. Then what happens? Momentum increases by 50%. So P2, final momentum P2 means initial momentum plus 50% of initial momentum, because momentum increased 50%. P1 plus 50% means 50 by 100, that is 0.5. 0.5 P1. This is P2 is 1.5 P1. P2 is 1.5 P1. So Ke2 equal to, we will get what? 1.5 P1 whole square. Instead of momentum we have to give 1.5 P1 whole square divided by 2m. 1.5 square is 225, so we will get 2.25. 15 square is 225. So here 2.25 into P1 square by 2m is actually Ke1. So Ke2 equal to 2.25 Ke1. That value you have to give. 2.25 Ke1 minus Ke1 divided by Ke1 into 100. 2.25 Ke1 minus Ke1 is 1.25 Ke1 divided by K1. K1 cancelled. 1.25 into 100 is 125%. Here this we got positive, so we will say kinetic energy increases 125%. This is the right answer. Okay, now next question. If momentum increases by 0.1%, then what will be the percentage change in kinetic energy? So here momentum increases by 0.1%. This percentage is very small, less than 10%, less than 5%, small value. So what is the equation of kinetic energy with momentum? P square by 2m. So if small percentage changes are given, then we can use the powers, multiplying with the powers, okay, as we did in the case of error analysis. Okay, if you are not aware of that error analysis, if you don't know anything about the error analysis, then you can watch our video of units and measurement, and the link is given below. Okay, so here we can say change in kinetic energy or relative change in kinetic energy equal to 2 into relative change in momentum. We can multiply with power 2 into. So here momentum increases 0.1%, so kinetic energy increases 0.2%. Just multiply with the power if the percentage change given is very small. Otherwise, you have to use the authorized method that we already did in the earlier question. Next point we have to study is potential energy. We can give symbol capital U or PE. Okay, potential energy. Potential energy is actually negative of work done by a conservative force. Potential energy is the negative of work done by a conservative force. Potential energy is defined only for conservative forces. Okay. For example, a body of mass m is raised to a height h. Work done by gravity is minus mgh because the body is raised against gravity. So, potential energy of the body is plus mgh. Gravitational force did a work minus mgh. Then the potential energy stored in the body is plus mgh, negative of work done by a conservative force. And if a non-conservative force is doing a work, that work will not be stored as energy. That work will be lost in the form of sound, heat, etc. Potential energy U equal to minus W minus integral f dot dx, and to find potential energy difference between 2 points, so we can say U equal to minus integral x1 to x2 f dot dx. Okay, this integration we should apply when there is a function, if force is given as a function of displacement. Okay, now listen here. U equal to minus integral f dot dx. Then from here we can say force equal to minus du by dx. To get potential energy, we have to integrate force with respect to dx, and we have to give a negative sign. So, to get potential energy from force, what do we have to do? We have to differentiate opposite operation of integration. We have to differentiate potential energy with the displacement. So, du by dx indicates change in potential energy. Du by dx indicates change in potential energy with position or displacement. It is called potential energy gradient. It is called potential energy gradient, and we can say the conservative force is negative of potential energy gradient. Conservative force is negative of potential energy gradient. If the conservative force is 0, then we can say du by dx equal to 0. Change in potential energy with position is 0. That means potential energy equal to constant. If potential energy equal to constant, there is no work. Work done equal to 0. So, we can classify the physical equilibrium into 3 cases: stable equilibrium, unstable equilibrium, and neutral equilibrium. Stable equilibrium, unstable equilibrium, neutral equilibrium. In 3 cases, force should be 0. So, change in potential energy with position is 0. Here also force should be 0, and here also force should be 0, because both are physical equilibrium conditions. Then what is the difference between these 3 equilibrium? A ball is kept inside a ball. We can say the ball is in stable equilibrium, and a ball is balanced at the top of a ball. So it is unstable equilibrium. Okay, this is an example. Okay, and a ball is placed on a table. This is neutral equilibrium. What is the difference? In the three cases, net force is 0 because the ball is balanced. But in the first case, in stable equilibrium, if we are giving a displacement, to the ball will return to the original position. Stable equilibrium. And here, if we are displacing the ball will not come back to the original position. It will move. It will get displaced far and far. Okay. And in neutral equilibrium, when we are displacing the body, okay, it will not get back or it will not go further. That condition is called neutral equilibrium. Okay. Then how to get the differences here? Here potential energy is minimum because ball lies at the bottom, height small, so potential energy minimum. Here potential energy maximum, and here potential energy same everywhere on the table, constant potential energy. If the body is displaced a little bit, body will get a force to come back to original position. That means body just as experiencing an attractive force from the original position. That means here change in force with the position is negative. Change in force with the position. dF by dx is negative, or we can say d square u by dx square is positive. Why we took dF by dx is negative? Attractive forces are always taken as negative and repulsive forces are always taken as positive. A simple example is in electrostatics. To understand, I am giving a simple example. If two charges q1, q2, if they are like charges, we will get force F equal to 1 by 4 pi epsilon 0 q1 q2 by r square. Like charges, repulsive force. And when one is positive and the other is negative, unlike charges, we will get k q1 into minus q2 by r square. So the value will be negative. Like that, you studied that vector form of Newton's law of gravitation and Coulomb's law for charges is always negative because it is attractive in nature for unlike charges, and for masses gravitational force is always attractive. So the body tends to come back to the original position so as the body gets an attractive force. So change in force with position is taken as negative, or d square u by dx square is positive because F equal to minus du by dx. And here the body will not come back to the original position. dF by dx is taken as positive, just like a repulsive force. Okay, or we can say d square u by dx square is negative, and here dF by dx is 0 and d square u by dx square equal to 0 because there is no any force to come back or to go further in neutral equilibrium. So change in force with the position is 0. Here change in force with the position is positive, and here change in force with the position is negative. So to understand which type of equilibrium? The equation of force we have to differentiate once with respect to dx. If it is negative, it is stable equilibrium. If it is positive, it is unstable equilibrium, and if it is zero, it is neutral equilibrium. Okay, here is a question. Potential energy U equal to A minus Bx plus Cx square joule, where A, B, C are constants and x is the position or displacement. Questions are position, what is the position of equilibrium? And question 2, which type of equilibrium is this? Stable, unstable or neutral? Okay, how to find? Answer. To find position of equilibrium, we know that force equal to 0. At equilibrium, force equal to 0. So derivative of u with respect to x should be 0. Then we have to differentiate. A is constant, no function, no x here. So derivative of A is 0 minus dx, d by dx of x is 1, so minus b plus cx square, c into 2x equal to 0. So minus b plus 2cx equal to 0, 2cx equal to plus b, x equal to b by 2c, x equal to b by 2c. This is the position of equilibrium. And which type of equilibrium is this? To find the equilibrium, we have to get df by dx. So to get f, we have to differentiate du by dx. F equal to minus du by dx, negative of what is du by dx? Here we already did 0 minus b plus 2cx. So we will get f equal to what? Minus of minus b plus b. B minus 2cx is the force. B minus 2cx is the force. Then df by dx, differentiating, derivative of b is 0 minus 2cx, 2c, we will get minus 2c. So df by dx is negative. If df by dx is negative, the equilibrium is stable equilibrium. Equilibrium is stable equilibrium. So once more, if potential energy is given, just to find its derivative and given negative sign, then it will be force. It is that conservative force. Okay, and if we are differentiating that force again with dx, if it is negative, then it indicates stable equilibrium. If it is positive, it indicates unstable equilibrium, and if it is 0, it indicates neutral equilibrium. Okay, and to find the position of equilibrium, du by dx or f should be 0, then x equal to b by 2c. Okay, that we will get from here too. B equal to 2cx, x equal to b by 2c. Next, elastic potential energy. Elastic potential energy. A spring whose one end is fixed and a movable mass is connected at the other end. This position is called equilibrium position or mean position. If it is given a displacement x towards right, a restoring force develops in it to come back to the original position. So direction of restoring force is always towards the main position. This is the main position, and the last point of the mass is called extreme position. Like that we can give x displacement towards left also, and here also the mass will have an extreme position. So the mass will oscillate due to the restoring force. That restoring force is also called spring force. It is conservative force, F equal to minus kx. F equal to minus kx. Force is given as a function of displacement. So elastic potential energy U equal to minus integral F dot dx minus integral minus kx dx, minus of minus plus k into x dx, integrating we will get x square by 2, or potential energy of spring is half kx square. Potential energy of spring is half kx square. At the main position x equal to 0, that means potential energy equal to 0, body mass reaches at main position. So displacement is 0, potential energy is 0, the restoring force is 0. And at extreme position, maximum displacement, maximum restoring force, so body possesses maximum potential energy and kinetic energy is 0. So we can say, we can draw a graph, energy displacement graph, energy on y-axis, displacement on x-axis. So the center position is main position, and here this is extreme position, here also one extreme position, extreme position, extreme position. Total mechanical energy means kinetic energy plus potential energy, both kinetic energy plus potential energy, their sum or total mechanical energy remains constant throughout the motion. This is the total mechanical energy, which is parallel to displacement axis. If body moves from mean position to extreme position, potential energy increases parabolically because potential energy proportional to x square. So shape of potential energy will be parabolic, and here also in this side also parabolic. This indicates graph of potential energy. And what is the graph of kinetic energy? What is the graph of kinetic energy? Total energy is same everywhere, so opposite. At the mean position kinetic energy is maximum, and at extreme position kinetic energy will be 0. Okay, this green line is the graph of kinetic energy. This is the energy displacement graph of spring, and in detail we will study it in oscillation. Okay, here is a question. A spring of spring constant 5 into 10 raised to 3 Newton per meter is stretched initially by 5 centimeter from the unstretched position, that is the initial displacement. So x1 equal to, we can say, 5 centimeter. Then work required to stretch it further by another 5 centimeter. So again it should be stretched by 5 centimeter. That extra work we have to calculate. Then what will be the total displacement? Total displacement is 10 centimeter. Why? 5 plus 5. So work done equal to change in potential energy, final potential energy minus initial potential energy, half kx2 square minus half kx1 square. So we can take half k outside, then we will get the answer. Now half into what is k, 5 into 10 raised to 3 into what is x2 square minus x1 square, x2 square, 10 square minus 5 square, centimeter square will be inside. Okay, so taking outside and converting into meter square, 10 power minus 4. So half into 5, no need of it. Okay, here 10 raised to 3, 10 raised to 3 by 2 is 500, 5 into 500 into 10 square, 100 minus 75 into 10 power minus 4 into 10 power minus 4, 2500 into 75 divided by 10 power 4. Okay, 10,000. 2 zeros are cancelled. In 100 there are 4 25s. So 75 by 4 is 75 by 2 is 37.5. Its half is 18.75. 18.75 joule is the right answer. Okay, here we have two special cases. Okay, in first case, two water tanks or liquid tanks. First tank contains height h1 and second tank contains height h2. Area of cross section, same area of cross section. Both contain same liquid. Density of liquid is rho. So to make their levels, liquid levels same, gravity does a work. 1 by 4 a rho g into h1 minus h2 the whole square. 1 by 4 a rho g into h1 minus h2 the whole square. And here we have a second case. Two tanks. One tank contains 2h height liquid, and here is a stopper or a block. When the block is removed, then what happens? Liquid levels becomes same in the two tanks. That work done is found using the equation a rho g h square. Okay, no need of studying the proof, just by heart the results only, it is enough. Okay, here is a question. A pendulum bob of mass 400 gram is displaced through an angle 60 degree. Find the increase in potential energy. Length of pendulum is given 1 meter. So we can draw the diagram. Original position of pendulum bob. This is length L. Center of mass of the bob and point of suspension, that separation is called the length of pendulum. Okay, and it is displaced through an angle 60 degree. This is the angle 60 degree, or generally we can give this as theta. Okay, then what is the change, increase in potential energy? This is the height difference of the bob. This is the height difference of the bob. So we can say change in potential energy, that is actually increase in potential energy, equal to mgh, because h is the height difference. And how to calculate h? H should be calculated this is L, right? This is L. L we can split into two components. Here this portion is L cos theta up to here, L cos theta. this portion L cos theta. So this length is also total L. So L minus L cos theta gives H. L minus L cos theta gives H. So H is actually L minus L cos theta. So change in potential energy equal to mg L into 1 minus cos theta. mgl into 1 minus cos theta. This is actually increase in potential energy, that means decrease in kinetic energy. Okay, now we can give the values here. Mass is 400 gram into 10 power minus 3. G approximately 10, 9.8. Length is 1 minus cos 60, theta is 60 degree, cos 60 is 1 by 2. You can give 10, 400, 2 zeros along with the 10 cancels, 10 raised to minus 3. 1 minus 1 by 2 is 1 by 2. So 4 into 1 by 2 we will get 4 by 2. 2 joule is the increase in potential energy. Now, if it is a meter stick, or a rod, then we have to consider the position of center of mass of the rod. So position of center of mass will be at length L by 2 from the point of suspension. So in our final equation, decrease or increase in potential energy or change in potential energy will be what? mgl by 2 into 1 minus cos theta, because for this length we have to consider position of center of mass from the point of suspension. So this is the equation for metal rod suspended at the top. Change in potential energy mgl by 2 into 1 minus cos theta. And for pendulum, string is assumed as massless. So no need of considering the center of mass or mass of the string. We have to consider only the center of mass of the bob. Okay, next heading is power. Power is actually rate of doing work, W by T. If work is given as a function of time, then power equal to dW by dt. If work is given as a function of time. Okay, and for work we can take vector F dot vector S by T. Displacement by T is velocity. So power is vector F dot vector V, velocity. Power is the scalar product of force and velocity. It is also scalar. Okay, the quantities that we are discussing in this chapter, work, energy, power, the three are scalar quantities. Now, so we can say when a constant work is acting, all objects are doing same work. Then we can say power proportional to 1 by T. That means the person who consumes less time has more power. Force F equal to mass into acceleration. Okay, for acceleration we can write m into dv by dt. F by m into dt equal to dv. And integrating on both sides, integral dt is t f by m into t equal to integral dv is v. So velocity equal to ft by m. Velocity equal to ft by m. We just discussed that power equal to f dot v. If theta equal to 90 degree, we can say power equal to f into force into velocity. For velocity, we can give what? F into ft by m. So power we will get f square t by m. Power we will get f square t by m. Here we can say same force or at constant force, power proportional to time. The person who can give constant force for more time, he possesses more power, and when lots of persons are doing same work, then the person does work within small time, has more power. So same work or constant work, power inversely proportional to time, and for constant force, power is directly proportional to time. SI unit of power is what? SI unit of power is what? 1 watt equal to 1 joule by 1 second, or 1 joule equal to 1 watt second. Watt second, watt hour, kilowatt hour. Watt into unit of time indicates energy. That's why we studied that kilowatt hour is the practical unit of energy. Okay, and there is one practical unit for power, 1 HP, horsepower. Okay, 1 horsepower equal to 746 watt. This is actually FPS unit of power is horsepower. It is equal to 746 watt. Listen here, power is constant, then force into velocity equal to power, it is constant. Okay, we are taking theta equal to 90 degree maximum power. Okay, for force we can write m into mass into acceleration into velocity, that is equal to power. Mass into acceleration is actually dv by dt into velocity equal to power. So v dv equal to power by mass into dt, integrating on both sides. Here v dv actually v raised to 1, so v raised to 1 plus 1, v raised to 2, v square by 2 equal to here p by m into integral dt is t. So from here we will get v square equal to 2 pt by m, and velocity v equal to root of 2 pt by m. Root of 2 pt by m, velocity directly proportional to t raised to 1 by 2, or v proportional to root t at a constant power. And what about displacement or position? Velocity we can write dx by dt. Dx by dt equal to root of 2p by m into t raised to 1 by 2. I took t out of the square root, so t power 1 by 2. Then dx equal to root of 2p by m into t raised to 1 by 2 dt. And here also integrating both sides. Integral dx is x. X equal to root of 2p by m constant into t raised to 1 by 2. What do I have to do? Differentiating, taking 1 by 2 into t raised to 1 by 2 Sorry. Integrating, integral dx equal to x equal to root of 2p by m constant into integrating, we have to increase the power, t raised to 1 by 2 plus 1 divided by 1 by 2 plus 1. 1 by 2 plus 1 is 3 by 2. So x equal to root of 2p by m into t raised to 3 by 2 all divided by 3 by 2, that 2 will go to the top. So x equal to, we will get root of 2p by m into 2 by 3 into t raised to 3 by 2. So we can say displacement is directly proportional to t raised to 3 by 2 and velocity is directly proportional to t raised to 1 by 2 at constant power. Now we can take this 2 by 3 into t raised to 2 by 3 by 2 inside the square root. So x equal to root of, when this 2 comes inside the root, it should be 4. 4 into 1, 2 is waiting inside the square root. So 4 into 2 is 8. 8p t raised to 3 by 2, we can write t cube inside the root. 1 by 2 will be adjusted with the square root. Okay, divided by 3 square is 9m. This is the equation for position or displacement of the vehicle at a constant power. Okay, both equations came number of times in various entrance exams. Okay, so the final result that you have to by heart. Coefficient of restitution. Small e. This is put forward by Sir Isaac Newton. What he told is coefficient of restitution is a constant. Relative velocity after collision divided by relative velocity before collision is called coefficient of restitution. According to Newton's law of collision, ratio of relative velocities of particles after and before collision is always constant. So that E is the ratio relative velocity after collision by relative velocity before collision, or we can say velocity of separation divided by velocity of approach. Before collision, particles will approach, and after collision, particles will separate. So relative velocity after collision is called velocity of separation, and relative velocity before collision is called velocity of approach. And E equal to, equation of E is V2 minus V1 by U1 minus U2. E is always a constant, positive constant. It will not be negative. That's why we have to write, if we are writing V2 minus V1 on numerator, we have to write U1 minus U2 on denominator. And you can write V1 minus V2 on numerator, then you have to write U2 minus U1 on denominator. So always E is a positive constant. E can never be negative. That is why a order change in the equation. In all types of collision, momentum and total energy remains constant. Total energy equal to constant. Momentum is also constant in all types of collision. Okay. And what is the difference between elastic and inelastic? In elastic collision, kinetic energy equal to constant. And in inelastic collision, kinetic energy not equal to constant. That is the main difference. Kinetic energy constant in elastic collision, kinetic energy not equal to constant in inelastic collision. Here, during elastic collision, kinetic energy before collision is same as kinetic energy after collision. There is no loss of kinetic energy in the form of sound, heat, etc. But during inelastic collision, there should be kinetic energy loss in the form of sound, heat, etc. So, kinetic energy after collision is less than kinetic energy before collision. Okay, that is inelastic collision. So, all normal generally occurring collisions are inelastic because sound, when two balls are colliding each other, sound is produced and heat is produced. So, generally all collisions are assumed to be inelastic. But collision between gas molecules, subatomic particles, neutrons, protons, electrons collision, they are assumed to be elastic. Okay. So here kinetic energy after collision is equal to kinetic energy before collision in elastic collision. So kinetic energy after collision is equal to kinetic energy before collision means relative velocity after collision equal to relative velocity before collision. Velocity of separation is same as velocity of approach because kinetic energy remains constant. So in elastic collision, E equal to coefficient of restitution equal to 1, and in inelastic collision, kinetic energy after collision is less than kinetic energy before collision. So velocity of separation is less than velocity of approach. So E less than 1 or greater than or equal to 0. Sorry, once more. E less than 1, greater than or equal to 0. Why greater than or equal to 0? If E equal to 0, what? If E equal to 0, that is perfect inelastic collision. If E equal to 0, that is perfect inelastic collision. Perfect inelastic collision means particles stick together after collision. For example, what is the equation of E? E equal to V2 minus V1 by U1 minus U2. To become E equal to 0, V2 minus V1 should be equal to 0. Here, magnitude of V2 should be equal to V1 or V2 equal to V1 equal to 0. To get E equal to 0, there are two possibilities. One possibility, both particles moves with the same velocity after collision. That means both are stuck together, moves together after collision. Or another chance is V2 equal to V1 equal to 0. That means both particles stick together and they remain at rest after collision. Okay, that type of collision is called perfect inelastic collision. In perfect inelastic collision, coefficient of restitution is 0. For example, mud is thrown to the wall. Mud sticks to the wall and after collision they remain at rest. That is an example of perfect inelastic collision. Elastic collision in one dimension, it is also called head-on collision. One dimensional collision, particles moves in a straight line. Okay, elastic collision in one dimension, mass m1 moving with velocity u1, mass m2 moving with initial velocity u2, and they collides, and after that m1 moves with velocity v1 and m2 moves with velocity v2, m2 moves with velocity v2. Okay, momentum before collision equal to momentum after collision, so m1 v1 plus m2 v2 equal to m1 u1 plus m2 u2. Momentum is conserved in all types of collision, and the kinetic energy is also conserved. Initial kinetic energy equal to final kinetic energy, half m1 u1 square plus half m2 u2 square equal to half m1 v1 square plus half m2 v2 square. By solving those two equations, okay, you got velocities. You already studied velocities after collision. Velocities after collision equation, v1 equal to m1 minus m2 by m1 plus m2 into u1 plus 2m2 by m1 plus m2 into u2. And velocity of second body after collision, m2 minus m1 by m1 plus m2 into u2 plus 2m1 by m1 plus m2 into u1. To remember this equation, when you are studying or discussing the velocity of first body after collision v1, you have to write first term with u1, and the m1 is greater than m2. You have to write m1 minus m2 by m1 plus m2 into u1 plus, okay, next term is u2, that is 2m2 u2, and denominators are always m1 plus m2, and to write v2, m2 minus m1 by m1 plus m2 into u2 plus 2m1 u1 by m1 plus m2. Denominators are always m1 plus m2. If masses are same, m1 equal to m2, then what will be equation of v1? What will be equation of v1? If m1 equal to m2, this term m1 minus m2 will be 0. First term will become 0, and here 2m2, 2m by m plus m, 2m, because all masses are equal, 2m cancels. Okay, v1 will be u2, v1 equal to u2, and what is v2 equation? What will be the value of v2? First term will be 0, 2m1 by m1 plus m2, 2m by 2m into u1, v2 equal to u1. Then what we understood here? Two identical masses collide elastically in one dimension, then their velocities are exchanged. They will exchange their velocities, and so they will exchange their kinetic energies each other. Two bodies of equal masses are colliding elastically in one dimension, and one body is at rest. That means second body is at rest. So one body is colliding the other body at rest. Identical mass, elastic collision, one dimensional collision. Then what happens? Then what will be v1? v1 equal to, this term becomes 0. This term also becomes 0 because u2 is 0. And what about v2? v2 becomes what? This term becomes 0, 2m by m1 plus m2 into u1, 2m by 2m cancels, v2 becomes u1. Then here what happens? When a body collides, when a body collides an identical another body at rest elastically, then what happens? First body comes at rest, its velocity becomes 0. And second body moves with the velocity of first body. Second body moves with the velocity of first body. That means the entire velocity of first body is given to the second body, and the entire kinetic energy of first body is also given to the second body. So here we can say 100% exchange of 100% exchange of velocity and kinetic energy in elastic collision of identical masses with one at rest. Ke exchange during elastic 1D collision. For first body, initial kinetic energy equal to half m1 u1 square, and for first body the final kinetic energy is half m1 v1 square, half m1 v1 square. So if first body gives kinetic energy, some kinetic energy to the second body, decrease in Ke or change in Ke, delta Ke equal to, we can give bigger minus smaller. Okay, kinetic energy initially is big, so we can say half m1 into u1 square minus v1 square, change in kinetic energy, half m1 u1 square minus half m1 v1 square, decrease in kinetic energy. So fractional change or relative loss, relative decrease in kinetic energy, delta Ke by Ke, change by original, half m1 u1 square minus v1 square by original is initial kinetic energy half m1 u1 square. So half m1 cancel, we will get u1 square minus v1 square by u1 square, or we will get 1 minus v1 by u1 the whole square, 1 minus v1 by u1 the whole square. This is the fractional or relative decrease in kinetic energy of first body if it gives kinetic energy to the second body. 1 minus v1 by u1 the whole square. If u2 equal to 0, that means if second body was at rest, then we will get equation of v1 equal to m1 minus m2 by m1 plus m2 into u1 only. No need of term of u2 because it is 0. So we can give instead of v1 by u1 m1 minus m2 by m1 plus m2. So fractional change in kinetic energy equal to, we will get 1 minus m1 minus m2 by m1 plus m2 the whole square. Fractional change in kinetic energy of particles in 1D collision. That means one body loses the kinetic energy, that loss in kinetic energy of a body is actually transferred to the second body. There is no loss of kinetic energy in terms of sound, heat, etc. There is no loss of kinetic energy in terms of sound, heat, etc. Kinetic energy just transferred from one body to another. That is why this collision is elastic collision. Okay, in some textbooks you can see loss of kinetic energy. Okay, that loss means one body transfers some of its kinetic energy to other. So first body loses the kinetic energy and second body gains. No loss of kinetic energy in the form of sound, heat, etc. This is elastic collision. So this is the kinetic energy transferred. Then what is the kinetic energy retained? Delta Ke by Ke retained, or the remained kinetic energy equal to m1 minus m2 by m1 plus m2 the whole square. 1 minus m1 minus m2 by m1 plus m2 the whole square is the kinetic energy transferred, and kinetic energy remained with the first body is m1 minus m2 by m1 plus m2 the whole square. Okay, that is all about collision in elastic collision in one dimension. Oblique elastic collision, it is also called a glancing collision because particles will not move in one dimension after collision, they move along different paths. Okay, that happens because before collision paths of center of mass of particles will not be along a same line. Okay, lines of travel are different before collision, that's why after collision particles move along different directions. Okay, what it may be, their direction of motion are same but their paths are different. Okay, so here m1 deviates with an angle theta 1 from the initial direction of motion, and m2 deviates theta 2 from the initial direction of motion. Okay, here theta 1 may be 0, theta 2 may be 0. Okay, this here we are representing general conditions. Okay, so initially both the particles have momentum along x direction, and along y direction they don't have momentum. Okay, initially, and finally after collision they have momentum along horizontally along x axis and along y axis, because their momentum is m1 v1 at an angle theta 1. So this momentum we can split into m1 v1 cos theta 1. Okay, and for second body m2 v2 cos theta 2. Okay, x axis components of momentum and y axis components of momentum. Here first body have m1 v1 sin theta 1 upwards, and for second body m2 v2 sin theta 2 downwards. After collision particles have momentum along x and y direction, and before collision they possess momentum along x direction only, m1 u1 plus m2 u2. So here we can apply momentum conservation along x axis and along y axis, and here also this is elastic collision, so here we can apply kinetic energy conservation. Kinetic energy after collision equal to kinetic energy before collision. So here I am writing kinetic energy conservation. So I can say a special case, I can explain a special case, that's why I am discussing here kinetic energy conservation. Initial kinetic energy half m1 u1 square plus half m2 u2 square equal to half m1 v1 square plus half m2 v2 square. For kinetic energy it is scalar, so no matter if their directions are different. Okay, half is constant, so half we can cancel out, common, half is common, so we can cancel out. If masses are same, m1 equal to m2, so mass also we can cancel out. And second body is at rest, that means if second body is at rest and first body hits the second body, then u2 is also 0. Then what will we get? u1 square equal to v1 square plus v2 square. u1 equal to root of v1 square plus v2 square. u1 is initial velocity of first body, v1 square plus v1 is final velocity of first body, v2 final velocity of second body. So u1 is the resultant of, magnitude of u1 is the resultant of v1 and v2. Vector u1 equal to actually vector v1 plus vector v2, because velocity is a vector quantity and their magnitude is given as root of v1 square plus v2 square. Then what happens here? What does it mean? v1 is perpendicular to v2. v1 is perpendicular to v2. So theta 1 plus theta 2 equal to 90 degree. Theta 1 plus theta 2 equal to 90 degree. That means when a mass hits elastically another identical mass, oblique collision, then they will deviate at an angle 90 degree. They will deviate at an angle 90 degree, and the resultant of their velocities after collision is equal to the magnitude of velocity of the first body or the colliding body. Inelastic collision in one dimension. In inelastic collision, E less than 1, greater than or equal to 0. If E equal to 0, it is perfect inelastic collision. So velocities after collision, V1 equal to m1 minus em2 by m1 plus m2 into u1 plus 1 plus E into m2 u2 by m1 plus m2, and V2 equal to m2 minus em1 by m1 plus m2 into u2 plus 1 plus em1 u1 by m1 plus m2. A small change in the equation that we studied for elastic collision in one dimension. The change is, for elastic collision we did E equal to 1. You just give E equal to 1 here, m1 minus m2 by m1 plus m2 into u1, and 1 plus 1 2 m2 u2 by m1 plus m2. The same equation, but we just inserted E in two cases, in two terms, in two manners. But this is the equation that we studied for elastic collision in one dimension, but instead of 1 we used here E, because E is less than 1. Okay. Now in inelastic collision we already studied that kinetic energy losses in the form of sound, heat, etc. So that equation is that kinetic energy loss is found using the equation delta Ke equal to half m1 m2 by m1 plus m2 into 1 minus E square into u1 minus u2 the whole square. In perfect inelastic collision, E equal to 0, then we will get loss of kinetic energy in the form of sound, heat, etc. half m1 m2 by m1 plus m2 into u1 minus u2 the whole square. This is the equation to find kinetic energy loss in the form of sound, heat, etc. in inelastic collision. Here is a question. In perfect inelastic collision of identical masses, the loss of kinetic energy is u2 equal to 0. That means second body at rest. Options are here: 100%, 50%, 99% and 60%. How to find? We know that loss of kinetic energy equal to half m1 m2 by m1 plus m2 into 1 minus E whole square. That no need of that term because perfect inelastic collision. So u1 minus u2 the whole square, here u2 equal to 0. So u1 square. Delta Ke equal to half into m1 m2 is m square, identical masses, by 2m into u1 square. 1m is cancelled. Delta K, loss in kinetic energy equal to half m u1 square. It is the initial kinetic energy of first body and second body is at rest. That is the initial original kinetic energy by 2. Half m u1 square is initial kinetic energy of first body. It is the initial kinetic energy because second body is at rest. So half of initial kinetic energy is lost. Half is lost means the lost percentage is 50%. So we can say in inelastic collision of identical masses with one at rest, 50% of kinetic energy is lost in the form of sound, heat, etc. We already know that when we are dropping a ball from certain height to the ground, the collision with the ground is inelastic. Kinetic energy losses in the form of sound, heat, etc. So the ball will not rise to the initial height. Some part of energy, mechanical energy, is lost in the form of sound, heat, etc. Height after nth bouncing. Height after n bouncings is found using the equation Hn equal to e raised to 2n into h0. Hn equal to e raised to 2n into e power 2n into h0. h0 is the initial height of dropping and velocity of free fall after n bouncings. Velocity of free fall after n bouncings is found using the equation Vn equal to e raised to n into V0. Vn equal to e power n into V0. V0 is the initial velocity of free fall. Velocity of free fall means velocity with which the body just hits the ground. Okay, no need of the proof, you just study the equations only. Proofs, derivations that you may studied when you are in higher secondary 11th standard. Here is the question. A body falling from a height of 20 meter rebounds from hard floor. If it loses 20% energy in the impact, then E is coefficient of restitution is. Coefficient of restitution, height is given here, so we can use the equation. Height after nth bouncing is e raised to 2n into h0. So Hn by h0 equal to e raised to 2n. So e raised to n equal to what? Root of Hn by h0. First bouncing is the question. 20 meter rebounds after losing 20% energy. So n equal to 1. So we will get E equal to what? Root h1 by h0. Okay. E equal to root of h0 initial height, that is 20 meter. And that is h1 height after first bouncing. It loses 20% energy, right? So if it falls from a height h, okay, that height is 20 meter, it loses 20% after bouncing. 20% energy lost means 20% potential energy is lost. 20% potential energy lost means mass, potential energy equation is mgh, mass doesn't get lost. Mass is always constant for a body. Mass is always constant for a body. G is also constant. Then change is only for the height. So height loses 20%. Energy loses 20% means height loses 20%. Then what is the 20% of 20 meter? 20% of 20 meter is 10% of 20 meter is 2. So 20% of 20 meter is 4 meter. So 4 meter is lost. 4 meter is lost. So the remaining height is h1 height after first bouncing, it is 16 meter. So equation of E, we can substitute here 16 by 20. 16 square root is 4 by root 20. 4 by root 20 is root 2 into 10. 4 by root 2 is 1.414. Root 10 is 3.162. So the correct value of root 20 is around 4.427. 4.427. Value approximately around 0.89. Friends, our chapter work, energy and power, chapter number 5 of crash program is finished here. A study material with some entrance points and questions with solutions is given in the description box that you can download and you can practice. By practicing those questions you will get clear idea about the concepts of the chapter. Next chapter we are going to discuss is system of particles and rotational motion, simply rotational dynamics. Okay, best of luck, keep going good, okay, and hope for the best.